so sorry for a small break, but I will make a small commercial advertisement for two things. The first one, we are organizing a workshop in Czech Republic. It's a traditional one, and usually we choose some nice places. Like last year, we have been using the former main seat of the Liechtenstein princes, a big castle which is a UNESCO World Heritage Preserve. So we will occupy the castle and have a conference there. This year, the venue will be monastery, originally from the 12th century. So this is where we'll have the lectures and the social dinners and all the things. And of course, we'll have some nice, Good. So the invited speakers for this year are Fernando Brandao, who already left this winter school to prepare to go to Czech. Daniel Burgard, Frédéric Dupois, Valerio Scarani used to be confirmed here on the webpage, but he's not coming. Simone Severini, he already confirmed he's coming. Peter Shore and Reinhard Werner, let's see. I mean, Peter Shore was quite enthusiastic when I discussed it with him in Cambridge, so he might be coming. And of course, Andreas, who comes always. So these are the dates you can find on the webpage. So if you want to take a look at the workshop, just take a look at this web page. It's cequip.eu, like Central European Quantum Information Processing European Union. And this is the year 2014. The registration fee is usually around like 300 euros. It includes everything. Accommodation, you have a social dinner every evening. We have a beer tasting. We will visit a wine cellar where you have a wine tasting. We'll have like 15 samples of the wine. It's a really popular event. And we usually have a traditional bike trip, you know, to make some refreshment after all the social excitement. I can show you maybe pictures from the year 2011 when it was taking part in the same place as this year. So this is the group photo in front of the monastery of the people participating in the conference. This is a small excerpt from the social program. So this is the wine tasting, social dinner. I will just zoom it a bit. Yeah. So as you can see, the lecture hall is quite nice, and the workshop is conducted in a very informal atmosphere. By the way, Claude, Stefan, this is Marcus, who is being thrown into the swimming pool. So these are the poster sessions. Last year we had a trip in the city train and things like that. Oh, well, so that's essentially all. And here you can see the typical wine tasting we usually organize there. As you see, the participants are very enthusiastic about the wine tasting. So I hope you will make it and you will apply for the CEQUIP and come. Also, I have an unrelated advertisement. Don't look at this, it might look tempting, but this program is already over. So this is not valid anymore. You can't apply for a position for 7,000 euros, it's already closed. So what we are having in Brno at my faculty, right now I'm doing my sabbatical with Andreas at Barcelona, but I'm coming back in the autumn, and we are opening actually a couple of positions in Brno. Here it's just one position. So there will be 1 to 2 postdoc positions opening in Brno. The senior one, the salary is 55,000 crowns, which is like 2,000 euros. It's pretty. How many euros? 2,100 euros. Which in Czech Republic is pretty nice. A big tapped beer in a restaurant is €1. Lunch is for 3 euros. A set menu, things like that. It's nice. Lunch is how much? 3 euros. The lunch special set, you know. Andreas can tell you. So if you want, you can ask Andreas or even Stefan.
And what about accommodation? How many euros?
Accommodation, if you want like 80 square meters flat, not far from the city center, it will be like 400 euros, 400 to 500. Good. So I have 1 to 2 positions, and if you are interested, you can write me an email, and the positions are opened until they are filled. So the senior position is getting like 2,100, and there will be also a junior postdoc position, which is much less salary. It will be something like 35,000, but it's still pretty nice living in Czech Republic. Okay, so that was the commercial break. Thank you for your attention, and now let's get back to Andreas. In the autumn, in the summer, there was the last call going on. And actually, one friend from Bratislava got it a year ago, and he was very not here, not lawyers, right?
Well, Andreas is writing. And to tell you, Tamil, there is a proverb which says, you don't wake up somebody who is sleeping hungry and say that we have no food.
Czech Republic is the promised land. And you can check it out during the Tech Whip. Anyway. Okay, so I wrote some things to recap from yesterday. So I want to just continue the discussion. So recall that I introduced this crazy looking expression here. That we call the sandwiched alpha relative entropy or divergence, or I mean, unfortunately, too many names for these kind of things. And I was just beginning to fill out this meta-converse substituting this particular quantity. So we made the observation that this guy. So the one important thing was that we could have this minimax theorem, so that we could. We had this upper bound in terms of divergence, and we could actually massage it a little bit to get a min of some auxiliary state and then a maximum. So since we are after upper bounds, look here, we have here the number of messages, so we like to upper bound this. Or equivalently, here we have the log of the success probability, so maybe you also want to upper bound this in other terms. So you get at least something interesting if you substitute something here. And so this happens to be, so if you then look at what you get here, you just have here n of rho and then sandwiched by some state or some operator. So this is minus minimum output alpha entropy of another channel, which actually yesterday I was a bit too hasty to write n prime. So let's write it as n with a superscript sigma star. Here where n sigma star is of rho is sigma star to the 1 minus alpha over 2 alpha, n of rho, and then the same thing, sigma star 1 minus alpha over 2 alpha. So this is not a channel, but it's a CP map. And I mean channel, sorry for this. So we have to distinguish sometimes, of course, it's important that maps are trace preserving because then they are preserving the probability. This one is just a completely positive map. But we know a lot of things also about non-trace preserving completely positive maps. Okay, so let's focus first on this part. So since I introduced it yesterday, I just wanted to repeat it here. So maybe this is all I need. Yeah, so I just introduced some notation here. I call this chi alpha of n. Why do I want to remind you of Kolevo chi here? Because first of all, we know that this divergence is bigger than the von Neumann relative entropy divergence. So that means, and so when we, so let me put like this, chi alpha tilde of n, this is larger than the min sigma, the max rho, and then we have the von Neumann relative entropy. And this one, actually, this is I didn't show this, but I want to leave this also as an exercise. This is equal to the Holevo information. And so for the exercise, you need minimax theorem. So you need to know again that you can exchange in a certain sense the min and the max here, sorry. On the other hand, we know that there is this upper bound. So the let's say we call the optimal sigma here sigma star. So that's actually going to be the same one that we put here later on. Then we have chi tilde alpha of n. So because it's a relative, it's this relative entropy, I put down yesterday some comparison theorems that showed, I mean, this sort of this chain of inequality that showed that d is less than d alpha tilde is less than d alpha, and then we have an upper bound in terms of d again, plus so we have a, sorry, no, then I put just the sigma star d alpha tilde of n of rho in sigma, and then I can upper bound this by the d alpha, the von Neumann relative entropy, plus an alpha minus 1 times a constant. And so, yeah, so maybe the organization of the board is not the optimal one. So we see that this chi alpha tilde, I mean, whatever this is at least as large as Holevo chi. So that was what I was saying yesterday. By substituting this new relative entropy, we make the left-hand side bigger, but also the right-hand side of this inequality, of this meta-converse becomes bigger. So a priori, it's not clear that we're actually gaining something. But we're not making it so much bigger because if alpha is close to 1, then it's almost the same. So this is equal to chi of n plus order alpha minus 1. So that's very important. So by choosing alpha close to 1, we can basically make this as close as we wish to what we know is the capacity, or at least what should be the capacity. Now, of course, I left out something. We want many copies of the channel. So we want to apply this to n copies of the channel. And so I get, which way around do we put this? Alpha minus 1 over alpha log 1 minus epsilon is less than or equal to, I bring the log n on the other side, so I'm assuming, of course, that n is as large as possible. And then I have this guy here. So I denote it as a chi because it's essentially approximating the Holevo chi. Minus log n. And so I just want to a bit painfully clear. So we have this. So now I choose to present the constraint as a bound on the success probability. So I mean our idea is assuming that the log n, sorry, 1 over small n log n is bigger than the capacity of the channel. And from the first day lecture from Friday, and I also think Graham mentioned this a couple of times, we know that this is the regularization of chi of many copies of n. Maybe I shouldn't write n here because it's not the same one. K. So then the hope would be that this here would be negative, because I mean what we learned from there is if you choose alpha close enough to 1, then this will be essentially the Hollywood information. So this is what we get. We get exponential. And then I want to write it as a negative exponential. So I mean, I want to extract an n, which makes sense because we know that this grows as order n, this grows as order n. So we extract an n. We have, sorry, there's something weird going on. There's probably I copied a mistake. I should pay attention a bit more. So we have this one, and then we have 1 over n chi alpha tilde. So this is very typical, of course, that we have to normalize some of this n copy information quantity minus 1 over n log n. So let's call this R, so because we want to consider a rate of some code. Oops. No, this goes the wrong way around. I want a negative one, obviously, so I have an R minus. So I hope we are all happy with this one. Yeah, so this is kind of what you want. That is actually what we would like to have, except that we do not know that this is positive, right? Because then we have something positive. Alpha minus 1 over alpha is positive. So it's just some number. And so then we would say, now let n go to infinity. Yeah, so that's very important for the logic. Of course, what I wrote here is true for every small n. But I mean, I want to conclude something like, oh, the error goes to 0 exponentially. For that, I would need to know that this somehow is not n dependent. But of course, it still has the n sitting around here. So I write some kind of a dream here, because it's maybe true, but it may only be known true in the future. So as I said, what we know is that R is bigger than the capacity. So so clearly here we are interested in the, I mean, to make sense of this, to make some n-independent sense of this, we have to get a bound, we have to get some kind of control on this sort of thing when the number of copies goes to infinity. So again, I write k here, 1 over k chi alpha tilde of n tensor k. And so so you see we have to choose alpha larger than 1, otherwise this is not positive. But we can make it very close, right? I mean, this alpha shouldn't depend on n, on small n. So if we knew that this is equal to the capacity, which is equal to this one here, and then I'm using the observation we made over here that this chi alpha tilde converges to Hollywood chi for a fixed channel. So for fixed n and fixed k, this is equal to lim k going to infinity, and then I put this here, alpha going to 1 over k chi alpha tilde of n tensor k. So I wrote it in this way so that you see that what we want is that we can exchange two limits. There is the limit of alpha going to 1, which we know that for a fixed channel, it will recover the Hollywood information. So in a sense, the capacity. And there is the limit of k going to infinity, which we need because we know that in general, this chi of n is not additive. That's something that Graham mentioned. In general, it's larger or equal, and we know examples where it's strictly larger. So it's known that we need this regularization, which is also the case for the chi alpha tilde. So these are not additive. This limit of k going to infinity is really necessary to understand the large n limit. So this is a dream. Because if the dream, well, the dream is of course always something good. If it were true, then we could choose alpha larger than 1 such that, because now these quantities here, they are always, when alpha goes to 1, this is going to chi, such that I assume that R is larger than the regularization of chi, so that means I can choose alpha such that R is larger than the regularization of 1 over k chi alpha tilde of n tensor k. And then this is positive. And so this, let's call this E here. Yeah, so that's kind of the dream. So unfortunately, we don't know if this is true. So this is that's the bad thing. So and that is why I will only present now an argument for a specific subclass of channels, for which we can make an argument that does not require one of these two limits. If we happen to know, for example, so it's kind of another dream, which we say, well, okay, if the world is bad, then let's just look at the part of the world that we like. There are those channels for which the capacity is equal to the Holevo chi. These are the additive channels. And it turns out that for many of those, we can do away with this part of the argument. So I want to show you how that goes. So the thing is, okay, so I want to just erase this part here. Sorry?
Yeah, the only doubt is that we know there's a limit for those entropies to in the limit alpha tending to 1.
Yes.
To the previous, without the alpha versions.
Yes.
But at this level, you say it is where it is not.
Okay, so I could have been more explicit. I think I wrote yesterday an expression for this constant. So the point is this constant is sigma dependent. I mean, it depends on the system you're looking at. So because sigma is chosen as a function of the channel, so actually it's channel dependent. And so the scaling of this constant is very bad. So you cannot just exchange two limits here. I mean, this will not work simply because as k goes to infinity, this constant explodes. So for fixed alpha, this right-hand side doesn't have a finite limit. That's why you cannot do it. So these inequalities are very nice for fixed channel or fixed dimension and so on, but they are not suitable for the regularization. I mean, this is just a technical point, if you want. So it's a trivial observation, but it's worth making it because it leads to, I mean, basically the major open question about these channel capacities. I repeat it, we know that this chi alpha tilde is not additive. This is in the same way that the Holevo capacity is not additive and many other things in quantum information theory are not additive. However, it could still be that there is a way of proving that you can exchange these two limits. If you could do that, then you are done. Then you know that this is lower bounded by something larger than 0. So since I don't know this, I'm looking for a substitute. And so first of all, one of the things you can always do is if some quantity doesn't work, you try another one. So we have already an upper bound on this kind of thing. We know that this is yeah, we can upper bound it by this minimum output entropy. So this minus S alpha hat of n. No, sorry. Now, yeah, okay. Sigma star tensor n. So I say it again. So this is minimum output alpha entropy, and sigma star is the minimizer of that we had to over here in this exercise. In this characterization of chi, actually, this I should attribute this. I didn't come up with this. This is was done by Schumacher and Westmoreland. Around 2001. So this formula here. So I want to just fix this sigma star here. I'm sorry about this. So it's the one from over there. And so for n tensor n, I don't know if, sorry, for n tensor n, I just use sigma star to the tensor power n. So caveat, of course, I don't know, or we don't know, if that's optimal. But it's definitely an allowed choice. Yeah, so I hope that my writing is big enough so that you can distinguish when I'm talking about a single use of the channel and when I'm talking about n uses of the channel. So the sigma star is defined as simply the optimal auxiliary state for a single use. I don't know if sigma star to the n is optimal for n uses of the channel, but it's definitely allowed one. So it will give me an upper bound. And I will substitute that one. And then I'm using, so then you should convince yourself that n tensor n sandwiched with the sigma star tensor n, this is the same as n sandwiched tensor n. And so this is what I put here. So, and now all we need, so that's kind of the cliffhanger that I'm picking up from yesterday, all we need now is an n and a sigma such that this guy here has additive minimum output entropy. Because then we can extract the n here. So let's see if I... Yeah, let me put this here. And so this, the right class of channels that we should be looking at for n is entanglement breaking ones. At least That's one for which we can say something suitable here. So recall that entanglement breaking was this here. It meant that whatever entangled state you feed into, whatever one arm of an entangled state you feed into the channel, this here has to be separable. And I don't remember if Graham talked a lot about this. I think he mentioned briefly this kind of class. So there's a fact. If you want, if you're not familiar with this, I leave it as an exercise. N is entanglement breaking if and only if N can be written N of rho equal to some I don't like this. And in such a way that the Mi form a P of M. And these are states. So N is entanglement breaking if and only if it can be interpreted as a measurement followed by a state preparation. And because I can always fine-grain this measurement as a rank 1 measurement, so I can always, even if one of these operators should be higher rank, I can break it up artificially into more outcomes, each of which is assigned the same rho I. I can actually write it also like this: sum of a j, alpha j, beta j, x. Yeah, so this is just writing the same thing with rank 1 with a rank 1 Krauss operator, P of M elements. So it's a kind of slightly different way of looking at it, because you can say, you see that this is that another characterization of entanglement breaking, if you want. It means that you can find a representation such that all the Krauss operators are rank 1. Okay, I leave it at that for the moment. Even though, actually, let me just put a last thing here. I hope I will use it later. In Graham's lectures, we already came across this notion, and also I used it on Friday. This notion of complementary channel. So when the complementary channel, so that would be trace over Bob. V rho V dagger, where N of rho is trace E. So the complementary channel of entanglement breaking N, these are called Hadamard channels. Now, this is a conventional name that someone came up with in the literature, and now we stick with it. So that it's simply a channel class defined as these are the complements of entanglement breaking. So then there is a little observation that we need to make.
Can you recall the definition of complement?
It's this one here. So
No,
in general, yes, in general. So in general, every channel can can be extended to an isometry. Yeah, and the channel is obtained by tracing out Eve. The complementary channel is obtained by tracing out Bob. Come on. So, yeah, it's better to have these pictures, I guess, in the end. So the observation is that N is entanglement breaking, then the sandwiched channel is also entanglement breaking. Why is that? Because, well, I don't know, maybe it's evident. I mean, the one way of looking at it is, what does the sandwich channel do? Well, I first have to apply N, and then I have to multiply the resulting state from the left and from the right with this sigma star power. So I just have a sigma star to the power 1 minus alpha over 2 alpha. And so that's just a local map. I mean, if it was separable here, then it's separable here. And so that's the proof. So let's forget about the dream, because we don't need to dream anymore. So I just recall what this here is in case we don't agree. So this is the minimum output. I mean, so this kind of thing, the log of trace rho to the alpha, that's the alpha Rényi entropy. So that's why we call this the minimum output alpha entropy. And so there is a result by King. Now probably I won't remember the. Oh no, here we are. So if M1 and M2 are entanglement breaking CP maps. So note that this definition doesn't require that the thing is trace preserving. I mean, it will be well defined for anything that gives me something positive here, because then I can raise it to the alpha's power. So for completely positive maps, this will be fine. Then this S alpha hat of M1 tensor M2 is equal to the minimum output entropy of M1 plus the minimum output entropy of M2 for the same alpha. Note that if I stick in a product state here, then because of the log, this is the sum of the two entropies. So the proof of King amounts to showing that the optimal state you can put in here, or a optimal state, is a tensor product state. In particular, this here is the trivial inequality, because I have an optimal input row for M1, I have another for M2. I can definitely try out row 1 tensor row 2 as a candidate state for the product channel, and it will give me the entropy equal to the sum here. So when I take the minimization, it's smaller. So this one here is sometimes false. That's the point. But not for entanglement breaking. Yeah, so now it's paying off that we are restricting to this class of n. We do not, of course, I do not know in this generality. I mean, entanglement breaking channel, it's a large class. Aha, so here's another little exercise. So I hope you are aware that the channels, I mean, or yeah, let's talk only about channel, about trace-specific one. They form a convex set. So my claim is, inside this convex set, entanglement breaking channel is a convex set that has positive volume. So EB is a subset of all CP, TP. So I mean, this is very important because I think this class of channels is the first one that was discovered that is not singular. So I mean, I mean, I could have lectured also in this course, of course, about additivity, but somehow I felt I wanted to talk more about more recent things. Additivity of these information quantities, I mean, the way we look at it nowadays, it's a very rare thing. So it seems rather difficult to define in quantum information a quantity, something, of course, entropic, because it has to be additive on tensor products. But then you have to have these typical minimizations or maximizations. These often turn out to be not additive. So then we learned that, okay, for certain classes of channels or for certain classes of objects, you restore additivity. Initially, these were just measure zero sets. I mean, even actually small parameter families. So that's why I mentioned this here. Entanglement breaking has actually positive volume. It's not very big for larger dimension, but it's there. So, and that also means that entanglement breaking channels are pretty general. So I cannot really say very much about a generic entanglement breaking channel. In particular, I do not know what this sigma star is from luckily, I hope. Oh, I did it already. So this optimal state here. But whatever it is, also the twisted, the sandwich channel is going to be entanglement breaking. And so by King, we have that this is minus n times output entropy of n sigma star. Minus, and then let me substitute here n times the rate. It's kind of we know anyway it has to scale with n. And so then finally we use the fact that now we're talking only about a single instance of the channel again. So again, at this point, now it's allowed that we think of alpha going to 1. When alpha goes to 1, I know that this here converges to chi of n for alpha going to 1. So let's say we choose. Of course, I don't want to take the limit because I still have this thing here of this alpha minus 1 here. So let's choose alpha larger than 1 such that yeah, okay, I just here we have the real line. There is somewhere chi of n, right? Then there is this quantity here, this function of alpha. Here is the rate. So my assumption is the rate is bigger than chi, because I mean that's kind of the regime in which I want to prove decay of the success probability. So I know that I can choose this minus s alpha hat of n twisted somewhere in between. So let's say it's minus s alpha hat n sigma star is less than r plus chi of n over 2. Yeah, so it's closer to here than to there. And so from that I get that the success probability is bounded by, as before, the exponential minus n alpha minus 1 over alpha. And then what do I have? I get I know that this difference here is bigger than r minus chi of r minus chi of n over 2. And now this is the end because this is definitely positive by assumption, right? Alpha is bigger than 1, r is larger than chi of n. So this proves the strong converse. This shows that indeed if the rate is larger than the capacity, well, actually it shows if the rate is larger than the Hollywood chi, then the error goes to 1. So it also implies as a corollary that the capacity is equal to the Hollywood chi. So I mean, this is something that we knew. So it's a corollary which goes back to Shor. So he was the first one to notice that for entanglement breaking channel, the Holevo capacity is additive. So here we get something, I mean, we kind of get this as an afterthought. We get a bound in terms of Holevo chi. The capacity could in principle be larger, but that's ruled out by this. As soon as your rate is larger than chi, the error cannot go to 0 anymore. In fact, it goes to 1 exponentially fast. Okay. Let me see. Oops. Okay, at least I will finish the Oh, I'm not using that. It was just it was a side remark. Oh. It was for relief. No, it's important to. I mean, I think it's important to realize that this is a large class. It's not just. I mean, and on the other hand, all the examples of non-additivity that we know, they are of measure 0 in the convex set of all CP maps. So it's an open problem. Which of the two is more common as a phenomenon?
So why, you said you mentioned you thought it was a generic non-additivity.
No, I mean, generically, we don't know anything, right? For most of the channels. So I think it's rather nice to see that, to reflect on the fact, without any consequences for the proof, that this is a positive volume for which we can actually say anything.
So that the conclusion can be deemed as non-trivial.
In a sense, yeah. Okay. If your notion of triviality is that of a measure theorist, that you don't care about measure 0. I mean, I think I would contest it because, I mean, for example, depolarizing channel are very important, even though it's a measure 0 set. But still, I mean, for example, okay. So here's an important thing. One of the ways in which you can see this is that actually, whatever your channel is, if you compose it with a sufficiently strong depolarizing noise, you will eventually enter, I mean, if the noise is strong enough, you will enter the set of entanglement breaking channels. So the noise doesn't have to be 1, but it is something. And so that means the line, there's on the line connecting an arbitrary channel with a completely depolarizing channel, there's always a small non-zero segment of entanglement breaking channels. So this implies this statement here. So the channels. What kind of channels do you get when you compose n with a depolarizing channel? Well, when you think what is a depolarizing channel, it's just with some probability you leave the state alone, and with some probability you replace it by the completely mixed state, right? So that means the channels that you get in this way, they are convex combinations of the original channel and the completely depolarizing channel. So composing with depolarizing channel, you obtain the line segment connecting n with the completely noisy channel, with a fully depolarizing channel. So the claim is close enough to the completely depolarizing channel, everything is entanglement breaking. So each line segment, from wherever you start, each line segment connecting to the completely depolarizing contains a small this whole interval contains a small line segment of entanglement breaking. So when you think about it, this has to imply this statement.
When you are at least in finite dimension, this should also be kind of directly related to the volume of separable states.
Yes, 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 indeed, of course, yeah.
So Andreas, here, how do you avoid these two limits interchanging?
Well, because of the additivity, because I don't have to take the limit here. I know that this is n times the one copy thing. So in fact, so that's kind of, I erased the dream there, but this is in fact the only way in which we know how to avoid this interchange of the limits. We just have to know that one of them, the regularization, is simply not necessary. I mean, I'm talking about the domain of the known. In the domain of our knowledge, this is how it goes. It could be true that you can prove somehow that you can interchange these limits, but the only way we have discovered methods to do this was simply by showing additivity. Okay, so I want to use the remaining time, or at least part of the remaining time, to talk about the complements of these channels, because they are also very interesting. So complementary channel, let's remove this here. Actually, now I will use this here. It will become relevant. Yeah, so when we talk about complementary channel, I mean, the best way is just go to the Church of a larger Hilbert space where everything is unitary, or more simplified, isometric. So I mean, of course, I can also think of this as a unitary by simply attaching another system here, prepared it in a conventional pure state. So I will just absorb this into the unitary, and then I get an isometry. So the important thing about this is that when you look at it this way, you see that the minimum output entropy of a channel and of its complementary, of a map, isometry, if n, and of course also the complementary is CPTP, and it's linear in general. It's just a linear, I mean, it's just a linear transformation. If n is not completely, if n is completely positive but not trace preserving. So the output of any channel is equal to the output entropy of the complementary channel, and the same applies to the map, to the complementary map. Why? Because the minimization you can show, so this is important, because inputs are without loss of generality pure in this minimization of the output entropy. The reason for that is that these entropies are concave, so the minima are obtained on the extremal points. But when you stick in a pure state here, you get a pure state here. And so the reduced state on B and on E, they will have the same spectra. And that means that any function, not just the entropy, any function that depends only on the spectrum must be the same. And of course, also the minimization will be the same. And so that implies, that was a bit stupid to erase this theorem of King. That implies, of course, also trivially that if channels are decompletive, the complements also will be additive because of this. I mean, because the values are simply all the same. And so you might be tempted to think that, okay, then I can play the same trick and I get also strong converse for all Hadamard channels. So before we go into this, let's first stop for a moment and think about these Hadamard channels, because I didn't do this here. And I think that none of the other lecturers discussed this in detail. So first of all, by definition, I mean, if I take this here as a form of the channel, I can work out the complementary channel. I don't know if you've seen this. If you know the Krauss operators of a channel, so let's say EJ, rho, EJ, dagger, then you can write this isometry, or more generally this linear map, as a sum of J. Maybe not E is not good, because we need KJ. So this X is on B, and then I have a J on E. Yeah, so this is this kind of always this canonical way of writing a dilation, a linear dilation, and then I get the complementary channel by just tracing out B. So for entanglement breaking N, are? Oh, these ones are orthogonal. Yeah. Actually, this orthonormal, in fact. So you see, when you trace out B, you get all the matrix elements of J and K. So you get a sum here of J and K. So it's somehow a very, I mean, the complementary channel, the way you write it in this form, is a very matrixy thing. And if I use these Krauss operators here, then okay. So what do I get? I get some kind of alpha. Okay, I hope I get this right. Oh, okay, let me do this again. So I have, oh my goodness, actually, oh, I see, that was a bit stupid, actually. I wanted to be smart. I used alpha and beta because I thought alpha should remind you of Alice, of input, and beta of output, but actually it's exactly the other way around. Okay, I'll leave it like this. I don't want to change the notation now. It doesn't matter. So we have these beta J rho beta K, and then I have an alpha K, alpha J. So you see, these are some kind of matrix elements of rho in a weird basis, because the betas, they form a P of M. And this is just a positive semi-definite matrix with something on the diagonal. Actually, there should be ones on the diagonal. So this, so this only depends on J and K. So this is a matrix form of rho, and then this whole thing is a Hadamard product. And this is maybe the motivation for this name of Hadamard channel. So Hadamard product of two matrices is simply matrix entry-wise multiplication. So yeah, this is just a way of representing rho, and then you're just multiplying each entry by some fixed value.
So which is the thing? I mean, often they call it Schur product.
Yeah, actually it's the same, Schur product. Yes, yeah. I think this, or Schur Hadamard or whatever. I mean, there are different names for this. Yeah. So I guess the people that gave the name, they liked Hadamard better than Schur. So and then maybe, so this is, of course, this is not so hard to work out. Again, if you're interested in some examples, that's maybe more important. I think so. Entanglement breaking, I guess we are comfortable with this measure prepare idea. I mean, we know that okay, we can come up with plenty of schemes. What possible Hadamard channels can you have? Well, okay, one of them, or an important class, is phase damping. I mean, it's the so you have your rho. And this goes to A, B, and then some lambda C and lambda C star. Yeah? So this is so just damping of the off-diagonal elements. In fact, when you look at this, the simplest Hadamard channels you can get is just choose any orthogonal basis of your input space. Then you can make this matrix representation. You just write rho as a matrix, genuine matrix, and you choose one of these Gram matrices of a set of vectors. And Gram matrix of a set of vectors is the same as saying is positive semi-definite matrix. So so here I'm just multiplying with the matrix that has 1 on the diagonal and lambda on the off diagonal. Actually, let's just put a real number. So
that matrix is a diagonal. What is it? So what some people sometimes call diagonal channel, right?
yes, yeah, exactly. So they are also this kind of another special subclass. Exactly. Another one is erasure channel. No, is it true? No, sorry, that's completely nonsense. Okay, no. Another interesting one is the quantum limited attenuator that Graham mentioned. So you have your input mode coming in, you have a vacuum, and so which way does it go? I never know. So this goes alpha, and you have a lambda alpha here on coherent states. And if lambda is, no, is that true? Sorry, I'm guessing a different program now. What did I want to? I'm talking about degradable channels suddenly. Yeah. It's also attenuated, so it's definitely not entanglement breaking. Exactly. Sorry.
The complement of this is entanglement.
No, it's just another attenuator. I mean, the one has lambda, one has lambda. Sorry, I was just confused. Yeah. Sorry. Okay, now let's leave it at this. Okay, there's these phase damping channels. I mean, it's. I'm sure there are some more interesting ones, but now I cannot think of them. Okay, so here's an exercise. Find others. And so maybe by afternoon I will remember some others too. Because I know that there are some interesting others, but I just can't remember how they go.
Classical noise Gaussian channels beyond a particular noise should fall into this category.
Yes. That's true. Yeah, actually that's true. So the quantum limited amplifier. The quantum limited amplifier. Yeah, okay, so maybe that's where the confusion came from. Yeah, okay, great. Quantum limited amplifier is an example because the complement is the phase conjugation, the physical approximation to phase conjugation, and that is known to be entanglement breaking. Thank you very much. Yeah, good. Okay, so there are some interesting channels. Actually, this is very important because these phase damping channels, they are pretty trivial from the point of view of classical information transmission. Why? Because if I just choose to input only computational basis states, they come out unchanged, and they are orthogonal. So I can definitely communicate very well just by, for example, phase damping is a very good example. So this would be just applying a sigma z. So what you do is you use eigenstates of sigma z, and that's good enough to achieve the capacity. So this quantum limited attenuator has a non-trivial capacity, and so yeah. Okay. So, okay, the point is we get this additivity, so it's kind of a corollary to the King result. So we should also get a strong converse for capacity of n and n Hadamard. But actually, it's not so easy. In fact, it's a bit hasty because remember what we needed in our argument was not only that the channel is additive, but also this sandwich channel. So what we need is that this guy here, this sigma star, is additive. And so, but in general, actually, this is what I want to say. In general, this is not Hadamard, nor, yeah. So this is a bit of a problem. So this we kind of, okay, I show you why that is. Okay, over here exactly, we had our yeah, let me draw it in the pure state picture. So we have some input state. So if I do it like this, I can get the action of the channel by tracing over E, and I get the action of the complementary by tracing over B. Now, okay, so maybe like this. Now we do this sandwiching, right? So we have our sigma star to the 1 minus alpha over 2 alpha. And so what I would like is, so I'm saying, I mean, obviously in the previous argument, if the channel is entanglement breaking, then after this here still will be separable state. I'm just applying this local filtering. Now I'm talking about the complement of an entanglement breaking channel. So what I would need is that these two, this sigma BAE, trace over V, trace over B, should be separable. Yeah, so that would guarantee that would mean that the map from here to B is Hadamard, and then I'm in the right kind of direction, and I have additivity.
Actually, so this is really a very, very clever way of seeing it.
Yeah, well, okay, so the problem is this action is not trace preserving. I mean, it's just a CP map. And so here, when I look at this one here, when I look at trace of B, so this is identity tensor channel, complementary channel acting on phi. This is separable. Then I'm applying a filtering on the, I mean, this is what it is really. It's a filtering applied to the purification. And so this here will change. In fact, there are examples where this can change from being separable to going non-separable, depending on what this x here is. Yeah, so if I write it like this, it's x, v, phi, v dagger, x dagger. So that makes a difference, and so that's why this one here is not true in this simple form, simply because we do not get enough additivity we want. So we have additivity for our original channel, but we need it actually for this sandwich guy. Nevertheless, we can save ourselves, and I will just use the last minutes to show how that goes. So this is the problem. So now we just remember, I mean, how we get away with it. We remember that ultimately we are interested in the limit that alpha goes to 1, or we are interested in the regime when alpha is close to 1. And that means that x here is close to the identity, because I'm raising whatever the sigma star is. Again, I will not be able to say much about this matrix. Whatever it is, I'm raising it to a power close to 0. So when I just choosing alpha close enough to 1, I can make x to be very close to close to the identity, and that means that this x n of rho x, I mean this is positive semi-definite anyway, this will be close to n of rho for x close to 1, and that means for alpha close to 1. And so we do get something non-trivial if we do not happen to be on the boundary of the Hadamard channels. Yeah, so n sigma star is close to n for alpha approximately 1. And so that so here's the thing. So that means that the complementary channel, the complementary map of this one here, is also close to the complementary channel here. Actually, so if you want, there is I can even give you a reference for this. Well, only that I don't remember all the details of it. I think I remember the authors Kretschmann, Schlingemann, and Werner. So what they were doing is they were looking at exactly this sort of situation, that they had a theorem that shows that the diamond norm distance between two maps is related in a very tight way to the diamond norm distance of the complementary maps. So why could that be good news? Let's assume that this complementary channel is not just entanglement breaking, but it's in the interior of the set of entanglement breaking channels. So if NC is in the interior of the EB set, so to make this a non-trivial statement, I needed to know that it's a positive set of positive volume. Then I will just choose alpha so small that this little perturbation here is still in the interior. Is still, let's say, entanglement breaking. And that means that this sandwich channel, or the original sandwich channel, is Hadamard. and we get strong converse. Yeah, so I deleted this bound, but you get exactly the same kind of bound. So you can essentially relate, you can get an upper bound on the success probability exponential in n multiplied by a constant, depends on this alpha, which now I can say very little about how small it has to be, because that depends how close I am to the boundary, and r minus chi. So that means we get, for basically all the Hadamard channels, except for the boundary, we get a strong converse. And so then it remains only to find the trick to also take somehow the limit to go to the boundary. So this, of course, is a priori a problem, because the closer this complementary channel is to the boundary of the entanglement breaking maps, the closer I have to choose alpha to 1. So I cannot just take the limit, because in the limit alpha will be 1. So we do another thing. We do the things that is kind of, yeah, it's in line with all these various dreams that I formulated. If you don't like the reality, well, just change it. So in other words, of course, I'll have to face a channel that is, so, So if NC is on the boundary of EB, well, I told you before that you can at least find other channels that are in the interior. So there's one channel that is in the interior, which is the completely depolarizing channel. So let's just move a little bit closer to this one. So if this is entanglement breaking, and we're here on the boundary, we know that there is in the interior, there is, how do we call this? Tau. This is the map that maps, the channel that maps everything to the maximally mixed state. And so I know that the entire line is entanglement breaking. And in fact, except for this one point, everything is in the interior. So let's say D 1 minus delta is 1 minus delta depolarizing noise. On the output of this guy here, so that would be E. Yeah, remember, we are looking at the complementary channel that goes up here. And of course, I want delta to be bigger than 0. So the composition of n complement with this depolarizing noise will put me on this line. This is now in the interior. And so I definitely get a strong converse. I mean, I get for the channel M. So what does this composition look like? So we have a V here. We have a B that I don't change at all. And then the depolarizing noise, of course, I can also think of it as some particular isometry that introduces, outputs another E here and some kind of B prime. So when I insist, I mean, the notation I introduce here is, I want that this is the complementary channel of what? Of this thing that outputs B and B prime. Right? It should be clear, because because the complementary channel, it goes here, and it goes here, and everything else is traced out. So if that is MC, then M must take as output the old output that we had plus something else. So this is kind of this very important observation. M is more powerful than N in the very operational sense that I can just forget about B prime and obtain the original channel. So it can be degraded to N. So this is a very important consequence. Now I want to go back without writing much. We want to analyze a code for the channel N, for this guy here. Actually, many copies of that one. By this observation, it will automatically be a code for M, because if I happen to communicate through M, there is also this extra register B prime. Bob simply has to ignore it and apply the decoding map that he has for the channel N to this register. So that means N of N epsilon for channel capital N is less than or equal than N of N epsilon for channel M. So, and for this one we have the strong converse. For rate C of M. But M is not so much different from N in the end, because all we're doing is we're modifying the complementary channel only a little bit. Right? So, if delta goes to 0, then MC goes to NC, and that means again, by this Kretschmann and Werner result, that M converges to N. So this one here is less than C of N plus some order delta, I would say, this delta here. And that's it. So we get a strong converse again. And why? Because now the trick here was we were just comparing the channel that we really want to target with another one for which we can already say something, and we're exploiting the fact that their capacities do not differ too much. So this means also we get strong converse for N. Yeah, so I guess I mean, after saying this once more, I will just stop here. So why is it okay to modify the channel? Because we want, for example, in the logic of that I presented before, we assume that we have a code of rate larger than the capacity. So I will just choose delta so small that the capacity of M is still smaller than the rate R. And then I will just invoke the strong converse for M, and I get a bound on the success probability. So that's how we do. So in this way, so it's a nice twist, I would say, that you somehow need to leverage the additivity twice. I mean, you need to leverage in another way, because you need this continuity argument on the level of the channels, and then you need it again on the level of the capacities. And okay, that's. I will stop here. So tomorrow I will try to talk only about quantum capacity, which actually I was hoping to start already today, but fine. I mean, probably will be a bit more faster lecture. I wanted to give you also some more problems, but I think I mean, these structure theorems, that might be enough to think about in the tutorial session, like this finite volume and so on. So yeah, that closes this part. So I mean, we're getting more, we're getting a bit more humble in our results. So in the very first lecture, I outlined, for example, how you get strong converse for all channels when you look at entanglement-assisted coding. For the classical capacity, without any entanglement assistance, we don't know that. We also don't know whether the strong converse holds in general or not. So I mean, for example, this dream of interchanging the limits that could prove it for arbitrary channels, potentially in a way that we don't even need to evaluate what the capacity is, which is interesting and promising. So I want to say this very clearly. So for memoryless channels, there is no example known for which the strong converse fails. So at this level, it seems to be more that we have some issues with our proof techniques, because they all rely on additivity, and additivity fails in general. And so I was just focusing on some part of the landscape of all channels where the additivity is sufficiently strong, where we have sufficiently strong additivity results to let us deal with this problem of the limit. And so one of the big problems is to extend this. So there is a long-standing conjecture that for qubit channels, additivity holds. And yes, yeah. And in particular for amplitude damping channel, which is a very interesting subclass because they have only 2 Krauss operators. So amplitude damping qubit channels, I think it must be the simplest channel for which additivity is still open. And there is a chance that these ideas that I presented here could eventually lead to a resolution, including even the strong converse. So that's a promising direction here, and that's maybe the main thing that one can do. And of course, the other one is potentially look at some of the channels for which we know that additivity doesn't hold. So like these Hastings channels, Hastings type channels. Of course, they are very nasty to analyze because they are in very high dimension. They are not concretely described. But these are the ones for which there is a chance that they don't have a strong converse. I mean, there might be, after all, a deep connection between additivity and strong converse. We don't know this. So I would say that's the other big direction in these sort of questions, to find reasons why or why not the strong converse should hold for all channels. And I must say I'm at a loss at the moment, because it's the intuitions that one might have, they all come from classical information theory where it holds. Actually, it's a special case. Entanglement breaking channel includes, of course, all classical channels. So we recover Shannon theoretical results here in a new way. Okay, and that's the end for today.